The first speaker is Nicola Carissimi from the University of Lille, and he will talk about enriched bicategories for enriched bicoends. So, Nicola, whenever you want, you can share your screen. I think you have the...
Yes, here it is.
Mhm.
Thank you so much. Do you see everyone?
Yes, I do. Yes,
Okay.
whenever you
Well, okay.
want.
Thank you so much for the invitation. And yeah, I'm glad to be here and share with you this work, which is part of my uh, PhD thesis and involves some construction that we can do in enriched bicategory theory for defining and work with the notion of ends and coends in this context. So basically, the things that we are gonna um, see today are the definition of monoidal bicategories, which will be the universe over which we can enrich bicategories. So we will treat enrichments, and then we will study some kind of symmetry that we can have on this base monoidal bicategory V, which will be a braiding, and that will allows us to define the opposite V bicategory and tensor product of V bicategories, and then eventually ends and coends in the proper context. So let's start simple. We want to understand what are monoidal bicategories. So we know that in category theory we can let's say horizontally categorify, in a sense that monoids are one object categories, and that follows easily from the definition. And we can also look at a vertical way to categorify, in the sense that we can see what the structure become if we cut out all the top layer morphism and we just use identities. So monoids become just a point, categories become just sets, but we can also categorify in this sense. And so we find the notion of bicategory, of tricategory. And we have also a notion of a higher categorification of a notion of monoid, which coincides with the notion of one object bicategory, which is a monoidal bicategory. And then eventually we are interested today in this thing, which could just be defined actually as a tricategory with one object, because we have a notion of a tricategory, which is given in the work of Gordon, Power, and Street. And we can, of course, just say that it's a tricategory with one object is a monoidal bicategory. On the other hand, we want to understand how it is constructed, what's inside. So basically, we can try to construct it with the vertical categorification. So we can recall then that a monoidal category is simply a category C with functors, identity, and product, and natural isomorphisms, which are the associator and the left and right unitors, such that we have the usual coherence, Maclane's coherence axioms. Okay, so that's basically the structure that we deal with in a monoidal category. And let's see what happens if we decategorify. What can we get if we replace here? If we vertically decategorify the notion of monoidal category, we find a set with instead of a category C, function instead of functors, and the top layer of our structure becomes the axiom of monoid. Okay, those who says that the product is associative and there's a unit that does what the unit does. So that suggests that in order to categorify, we take axioms, these for the axiom monoid, and they become some structure that itself satisfies some axiom, which in the case of a monoidal category are the identity and associativity coherence, and in the case of a monoidal bicategory will be different axioms for the structure. So the vertical categorification then involves, of course, a bicategory C, and the functors become pseudo-functors, which are notion of morphisms of bicategories. Then ALR will be some pseudo-natural equivalences, which because there will be morphisms of pseudo-functors, and then the two axioms become structure. So we will have invertible modifications whose components will fit the two McLean coherences axiom. So a mu and a pi, whose component fit the IC and AC, the identity and the associativity coherence axioms. These two structures will be subject to other axioms. Especially, we will have well, first, in order to deal with this axiom, we will represent this object as string diagrams, because you will see soon that there's plenty of object and structure going on. So this is a language that helps a lot. You see, well, let's focus, for example, on pi. You have the source, which is 1a after a1, and we put it on the top, and we put on the bottom the target of pi. So we read the two morphisms from top to bottom, and we compose one morphism from left to right. And then this thing can compose, and there's a whole theory of string diagrams that that helps a lot in computations. So once we represent our structure, our modification in this way, the axioms become this one for pi, which is called the non-abelian four-cocycle condition, and is a higher analog of the associativity coherence. The name comes from the fact that this looks like a four-cocycle, more or less the same way the pentagon, the associativity coherence, looks like a tricocycle. If you write down the definition of a tricocycle, you will see that it will tell something like sum of three things, which are the source of pi, equals to the sum of other two, which will be the target of pi. And non-abelian, because of course here is the composition, it's not a plus. We're not in an abelian group. So that's one axiom, which is, as I said, a higher dimensional analog of the associativity coherence. And also, actually, other two axioms involving the identity. I mean, it's not the point here to understand what precisely they want, but just to show you the type of object that you deal with while working with monoidal bicategories. And it will be the higher dimensional analog of the identity coherence. Here we see some structure that you can define. It's gamma and delta. You can define them starting from pi and mu. What is the point? One of the main point of the theory of monoidal bicategories, which is one of the main point of the theory of tricategories, is the lack of strictification result. That's the situation. A bicategory is biequivalent to a two category. So a bicategory where the composition is strictly associative and the unit is strictly unital. And but this doesn't hold for tricategories, and not even for the one object case of monoidal bicategories. So what we can do is to strictify, but up to a certain point. So now I'm going to show you the point to which we can strictify a monoidal bicategory. And that will also simplify a lot the computation, okay? Because then we will assume often that some part of the structure is strict, is the identity. So here's the picture. We have monoidal bicategories, and we want to strictify along this continuous line up to a certain point that guarantees expressivity, that guarantees the fact that we have a proper notion of equivalence between the two. And we cannot reach monoidal two categories. Let me tell you why. And in order to understand why, we can we can think about the one object case. In fact, so the question is, what is a monoidal bicategory with one object? Let's put ourselves in a monoidal bicategory with one object, which is called a star. And let's consider a morphism, two morphisms, F and G, of this monoidal bicategory, which goes from star to star. Then we can tensor star with star and consider this diagram. And the fact that the tensor is a pseudo-functor will provide an isomorphism that fit this diagram, this square. But since we are at just one object, tensor star is just star, and under this equality, one tensor F becomes F. So here what we got actually. And when we look at the structure that we find by looking at one object, monoidal bicategory, what is a monoidal bicategory with one object? So it's what we can call a monoidal category. And in this monoidal category, the tensor product is given by the composition, as we know. And then these isomorphisms become precisely a braiding. Okay, something that switches the tensor product GF and the tensor product FG. And so the point is that on the other side, that diagram, if you are in a monoidal 2 category and the tensor is a strict 2 functor, well, the diagram is commutative. So what we find when you look at the monoidal 2 category with one object is what we can call a commutative monoidal category. If you want a braided monoidal category where the braiding is the identity, and that's a lot to require, and that's something that doesn't hold true in the sense that we cannot always strictify a braided monoidal category to something where the braiding is the identity on the object, you know. What we can do is that we can strictify the monoidal structure, but the braiding remains a braiding, okay? So that's the point to which we can strictify strict monoidal categories with the braiding. And the multiple object version of this is what is called a gray monoid. So the point to say all these big parentheses was just to say that usually when you work with monoidal bicategories, you actually can work with gray monoids. And the story, of course, works on one level up, and one can also define gray categories, which are the point to which we can strictify tricategories. Basically, one can imagine, for a gray monoid, one can imagine a monoidal 2 category. But when we have a tensor pair of morphisms, we can't talk about F tensor G, but we have to pick either one tensor F after G tensor 1 or the other one, knowing that they are isomorphic in a nice way. So in terms of computation, then for our purposes, everything works fine. So let's enrich something over this thing. Over a monoidal category, we can define the notion of enriched category, and the same we want to work for. We want for bicategories. So these objects were introduced by Gardner and Schulman in 2015, and one can imagine. One can think of them as generalizing the horizontal categorification, which is given in the case in which V is a cat with its Cartesian monoidal structure to the horizontal categorification that passes from monoidal categories to bicategories. So what are monoidal categories? Are pseudomonoids in cat. So in a general V, we want this kind of horizontal categorification. Well, let's come to the definition of what a V bicategory is. We have objects, we have home objects, which are objects in V. We have one morphism in V, which give unit and composition, and two isomorphisms, alpha, lambda, and rho, which are no longer natural isomorphisms because V is not necessarily cat, which have this usual shape that we can recognize also from the definition of a monoidal category, which is an example of that with one object and V equals cat. So what does this thing satisfy? of course, the identity coherence and the associativity coherence axioms, which can be written like this in string diagrammatic form. And you can recognize in orange the cells that gives you the triangle shape and the pentagon shape, typical of the identity and the associativity coherences. So I mean, one lambda after alpha equals rho one, and the pentagon on the other side. So now the point that we want to do, the step further with respect to the work of Gardner and Schulman that introduced this notion, is to put some symmetry on this, some sort of symmetry. In their article, they highlight the fact that they assume no kind of symmetry on V, and they are still able to define a lot of things: presheaf categories, limits, colimits, pointwise scan extension. Our case is in our case we want to define also opposite categories, opposite V bicategories and tensor product of V bicategories. So we do that, and we will verify that it works. And we need that because we want to define coends. So a sufficient kind of symmetry for this purpose is a braiding. Then what is braiding on a monoidal bicategory? We have a V with its tensor, unit, ALR, and the structure fitting the usual MacLane axioms. A braiding on V is a pseudolateral equivalence, beta, that switches tensor pairs. And if it were a monoidal category, now we would say such that two axioms, which are the hexagon axiom, which says that we can switch an element tensor with a pair by switching it directly with the pair, or either by switching it with one element of the pair and then with the other one. Now we are in a monoidal bicategory. I guess I think you'd guess that at this point this axiom will become further structure. So structure of a monoidal bicategory will be two modification, R and S, whose components fit these two hexagons themselves. R and S satisfy some axioms. Okay, axioms of braiding are huge and fairly complicated. Are these four? It's not the point to understand what they say, but also it's nice to remark that if we strictify up to a certain point, like if we assume that V is not just any monoidal bicategory, but a gray monoid, then the structures simplify because you have a lot of instances of pi, which is the pentagonator, the thing that fit the pentagon axiom, which will become the identity. Okay, so it will be something more about just R and S. Then what can we do with the braiding? To construct tensor opposite and tensor products of V bicategories. The opposite of a V bicategory C is C op and is defined by same object. Of course, home object C op xy is as usual C yx. Unit and compositions, well, the unit is really the same one, and the multiplication, like the composition is which is the term before applying the multiplication for C, because it needs that. It needs some sort of braiding. And then associator and unitors are defined in terms of the associator and unitors for C, as well as the braided structure. So the R and S and the part of the monoidal pi and mu and the thing from the monoidal structure of V. That we can assume to be strict at some point, but well, R and S it remains. So we have a proposition that just says that the identity coherence and the associativity coherence hold true in this for a COP, so that COP and this data eventually define a V bicategory itself. Sort of the same thing happened with the tensor product. If we have two V bicategories C and D, we can consider, well, as object the pairs of objects. As tensor product, as home object, this tensor product in V of home object. Oh yeah, there's a typo, that's D, a YY prime. And unit and composition. Here again, the composition need some sort of braiding. We need to switch to middle terms, to tensor the middle terms for defining the composition. And as before, the new alpha, lambda, and rho for C tensor D will be defined in terms of alpha tensor alpha for C and D, lambda tensor lambda for C and D, rho tensor rho, and the braided monoidal structure of B. Again, one has to check, and that's kind of a lot of computation, and in string diagrammatic formalism that identity and associativity coherence actually hold true in this case. So there's a remark at this point that I'd like to do, which I call the braiding versus coherence. And it's the fact that we have this phenomenon which improving the two proposition that I stated before, which are the fact that C op and C tensor D are in fact two V bicategories, and is the fact that when we try to prove the identity coherence, the braiding is required to be an equivalence properly. We need to use the pseudo inverse of beta. And on the other side, we make no use of the braiding axioms in defining, in proving that both C op and C tensor D are V bicategories. But on the other side, let's say orthogonally, when it's time to prove the associativity coherence, we don't really make use of the invertibility of beta. And we require, on the other hand, all the braiding axioms, which, by the way, do not require either the invertibility of beta. So this suggests that we could make that work also with a sort of lax or non-invertible, let's say, braiding. So I mean, I don't know where this brings. It was just a remark, and I think it may be worth to better understand why that happens. Then eventually, well, almost eventually, we can define, we can consider enriched pseudo functors once we define them, going from C op tensor C to D, because we have the op construction and the tensor product construction. And for these pseudo functors, which may start from C op tensor C or B op tensor D or any other V bicategory of this form, we can consider the notion of extra pseudo natural transformation, which will be basically consisting of indexed map from PCC to QBB, together with a higher structural morphism satisfies some axioms. We can also gather these objects I into a category because we have a notion of morphism between them. This category we may call well, the category of enriched extra pseudo-natural transformation from P to Q. And well, the term extra comes from the fact that, yeah, we are allowed to, as I was saying, to compare different categories. You know, in the domain, we can have a B tensor B op tensor B or C op tensor C. It justifies the target to be the same. And in particular, that's a way to get around a problem in enriched category theory, which is the fact that we don't always have a constant functor. And so in the bidimensional setting, the problem is the same, but we have a unit V bicategory, which is a bicategory with just one object and the unit as a home object. And from that, or equivalently from that J op tensor J, because they are equivalent, we can consider a constant functor, okay? We just pick an object in the target V bicategory, and then on the home object is defined to be the unit of this object in D, okay? So we can talk about constant functor when we talk about extra natural transformation. And this leads us to the defining V coends. Again, as also in the one categorical enriched context, we first define coend valued for functors, V pseudo functors here, valued in V, because there's the well-known thing that co-limits and limiting co-cones doesn't coincide in the enriched context. So if V is closed, that means it means a lot of things that I didn't tell you, but we have a notion of adjunction in this context. We can develop it and we can define what closed means, and we can see that if V is closed, it has a structure of V bicategory itself. Well, we can consider a pseudofunctor P of this sort, and a bicoend for such pseudofunctors is an initial extra pseudonatural transformation into a constant V pseudofunctors. What does that mean? Basically, it's an object in V, which we denote with the integral sign as usual. And we consider with that a structural extra pseudonatural transformation from P to the constant pseudofunctor with this value, and such that for every other one, we have a pair for every other one J going into X. We have a pair J tilde and a family of isomorphism, two isomorphism JC, indexed by object in B, fitting this triangle, okay, witnessing in some sense the initiality, and satisfying two axioms, which are two axioms that I managed to write down in translating the axiom were given for plane bicoends in a work of Alexander Corner in his PhD thesis in 2016. But then we realized that we have a more conceptual description, and which consists in this proposition, and says that for every x in V, for every object x in V, there's an equivalence which is pseudonatural in X between the categories of morphisms from the coend to X and the category of the pseudonatural extra pseudonatural transformations from P to X, which is just, well, it's given. If we look at here, it's given, well, if you take an F from the bicoend to X, you can construct an extra pseudonatural from P to X by precomposing with the structural I. And in fact, the two axioms that all that structure satisfy is just, if you write that down, just says eventually that this comparison functor is fully faithful and essentially surjective. So you have this equivalence. And eventually, now really eventually, one can define bicoend for arbitrary valued pseudofunctors. So it would take value in any V bicategory D and not just the closed V representably. That means, what is the bicoend is an object in D, such that for every other object in D, the extra pseudonatural transformation obtained by applying the contravariant Ohm functor from D provides a biend for that V pseudofunctors, which is V valued and for which we have defined yet biends and bicoends. So that was everything. I leave you some references some of the main thing on which the work is based. And I thank you so much for listening.
Thank you. Thank you. So it's question time now. You can silently upload. If you want to ask a question, just unmute yourself and go. I see that Adrian has a raised hand.
Yep.
So
Thanks. Firstly, thanks for the talk. It was very interesting. I have a quick question regarding so the notion of coends in this context. So in the ordinary enriched context, another way to directly get the notion of a coend is to say that it's a co-limit of like weighted by the Hom of a category. So presumably that also kind of gives a direct notion of coend in the bicategorical enrichment context as well. Is that something that kind of falls out of the formulation that you gave?
Yes, yeah. I mean, you're right. That's true. And I mean, I try to work in this setting by avoiding all the machinery of enriched by colimit, weighted by colimit. But yeah, it works. I mean, me personally, I checked that with specific cases of V where we can know how to construct the proper notion of limits and colimits. But yeah, it should work.
Great. Thanks.
anyone else? Ivan?
Um, so I wanted to ask about examples that you have in mind or if you want motivations for your work, what what do you have in mind?
Yeah, I was moved by a motivation actually in dealing with this kind of stuff, which is well based on the fact that if V is the category of additive categories, let's say, that is a monoidal, it has a monoidal structure. One can define by completing and, and everything. And I was motivated by defining a convolution product on a bicategory of pseudo functors from a bicategory enriched over add into add. It is the theory of Mackey two functors that leads to this situation because well, that additive bicategory I told you right now is a universal object for this kind of pseudo functors. And then, well, it's nice to define this object as just object in this functor, but we wanted a monoidal structure, and the proper way to define it was the deconvolution. So that's where ends and coends were needed.